So it's
Oh, scheiße. Before I kill myself. All right. So what's on the top here? Oh, okay. So A dot B. So it'll be 3 minus 4. I love it. So negative 1. And on the bottom is going to be the length of what? A, because, again, it's really easy. If it's B on A, then A is on the bottom. So what's the length of A? Square root of 17? Yeah. So is that, so the length of A, real quick, the length of A is square root of 17, right? And the length of B is square root of 10. That is much smaller than either of those. Do you agree with me?
Yes.
Right?
Yes.
Okay, which means what? When would the shadow of one on the other one be really small?
If it's the top one's really high.
Tell me.
Is the direction is
Then the angle is closer to 90. When they're close to, if it was exactly perpendicular, there would be no shadow. This would have been 0, right? Because if they're perpendicular, what's A dot B? 0. If they're perpendicular, the dot product is 0. Because dot product is all about one vector lying in the same direction as the other one. So when is the dot product 0? When they are 90 degrees apart. There is no component of one lying in the direction of the other one. So if I did calculate the angle of this, it's probably going to be something close to 90. I'm curious. Well, maybe we can do that. Anyway. So what's the projection going to be? Well, what's the first thing I write? I already got it, right?
wait, that's opposite. Yeah. So it's
Oh, I didn't. Oh, I was evil.
yeah.
I was more evil than I wanted to be.
Well, it's still the first part.
But I love it. I love it. You ready? All right. I didn't really mean that, but oh well. Look what I did. I was evil. So to get A on B, the only difference here. Square root of 10. Let me stop there for a second. Let me make sure. I actually did not mean to do that.
Okay.
But it's great. It was a great place to be evil. So you got to really pay attention. You know, be better than me, than I was right then. This is A on B, so what's going to be on the bottom is the length of B. The top is A dot B no matter what, because A dot B equals B dot A. And then what goes next?
1. Well, it's going to be -1. And, well,
No, it's going to be
so it's 2 things, so it's a vector times.
What's the vector B?
-3, 1.
-3, -1. Be really, see right here? That's the vector B. So then you just write the vector B divided by square root of 10. So you just now, how can I make this both rad 10 times rad 10? 10. I like it. So then I get negative. So that becomes 3/10 comma 1/10. Kick ass. So that is the vector that would describe the shadow that A makes on B. Okay. Just to put all that in words. Thank you so much. Thank you. I'll be here all semester. Yes.
Okay, so with those numbers, how do you get without an actual...
I'd have to give you an angle. If I didn't give you the components... So Jesse's got a good question. He said, all right, you did all this shit without components. If I didn't give you any components, I'd have to give you the angle between, because that's the only other way we know to calculate this, right? I like it. And some idea of what the lengths are. And then I have to give you a lot of stuff. Here, you can just calculate the stuff yourself. All right, let me stop there for a second. Yes, ma'am? Yes?
Does the negative sign component be on A mean anything?
Where are we at? Sorry?
The component of B on A.
Oh, does this negative sign mean anything? Well, it's a little weird, right? Because it's supposed to be a length, but it's sort of like this situation, if I shine a light straight down, isn't the shadow that's going to be, that's the extension. If they're not right on top of each other, if they're like this, then it's like a negative shadow. Does that make sense? So the negative really just means direction here. So don't freak out that this is supposed to be the length and it comes out negative. That negative actually has more to do with the direction it's pointing in.
So there's like negative like that, we know the angle between them
Is more than 90. So now I'm curious. Let me see if you guys can go back a step. Can you figure out the angle between those two vectors?
Yeah.
Somebody might have already done it. Yes, of what? We're missing something. Yeah, be careful. So it's almost this, except I need both lengths down here, right?
You just multiply those.
So, you guys are awesome. I think you're starting to realize that I'm going to expect you to remember a lot. Oh shit. What's up with this dude? You have to start making connections between all the things. So you only have to memorize 3 things instead of 50. If you need help with that, you can always come see me. So I know. What's happening?
8 times b.
Yeah. But to get the cosine, so to get the angle, it'd be the inverse cosine of
8 times b. So
A dot B, the dot product of A and B,
divided by
the length of each. So you don't want to do this, you want to do -1 over square root of 17 square root of 10. Right? Do the inverse cosine of -1, because that's A dot B, square root of 17 square root of 10.
94.4 degrees.
Sweet, look at that. So it was a negative projection, which meant it must have been bigger than 90, so it's got that shadow in the other direction. It was negative, and we knew it had to be close to 90 degrees because it's such a small length that the shadow makes. 94 degrees. Bam. I love that shit. I love it when it comes together. So you can look at most of these problems in 2 ways to make sure it makes sense. You can look at it purely mathematically, and you can look at it geometrically. All right? It's nice so you can double check and make sure it makes sense both ways. Okay. So I know this is new to you, but this is not as difficult as it might sound right now. This all comes off of that definition of dot product, everything we did today, basically. Yeah, sorry.
So for B onto A, not B onto A, how come, so you're looking for the projection of B.
On A. So this length has to be the length of A.
So that's why you need to do more.
This one has to be the length of B. Is that cool?
Yeah, I got it.
All right, I like it. It just takes some getting used to, right? And you're like, yeah, sure, everything does.
I have a question.
Yes.
So does the dot product being negative, positive, or 0, it obviously has to do with the angle. So if it's negative, if the dot product is negative as a whole, like
Good. If the dot product is negative, what must be true? Like, would these have a negative or a positive dot product? Positive. Because they both generally go in the same kind of direction, right? This would have a dot product that was 0. So it makes sense that would have a dot product that is negative. Now, if I start to swing it past 180, then I just flip it and it's the same damn things. Does that make sense what I just said? There's nothing above 180. Because then you just measure the angle. It's always the less than 180 degree angle we're looking at. Is that cool? What would the dot product of this be?
It would be the vector.
What's the dot product of this? Negative. And now I'm just taking that further down. So the dot product of that is still negative. I like it. All right, let's do a couple of quick specific examples. So everybody got what they want from... Well, I love this. Look at this shit. This is where people go a little insane, because you look up here and you look at everything and it's like, holy shit, but you look at each piece and you're not as holy shit. Yes?
You got the shrink of 94.
Oh,
Basically subtracted by 180.
you did an extra -1. I mean, there's only one. for one thing, and I think you have minus too many
I
parentheses.
thought you said it was multiplied those two.
No. It's the dot product,
Okay, it's just that.
which is the same.
I got you.
Yeah,
I got you.
okay,
Thank you.
okay. All right, so watch. What if I had this vector? What's the angle between those two vectors? Draw those two vectors for me. 2D, right? So don't freak out. Draw those two vectors for me.
0.
Draw me like your French vectors. Draw this one. Oh, there you go. That was freaky. I liked it. Strange retelling of that movie. All in mathematics, I like.
Hitting the iceberg effort.
Ice squared. Oh, sorry. That's horrible. Ice squared. Things are getting real now. All right, now come on. Have you drawn them yet? It shouldn't take long. 1, 2, 3, 4. Here's A. I'm going to put the A. And here's B. Is that cool? That's it, right? So what's the angle between them? 0. And dot product, what trig does it have in it? What trig function does it have in it? Cosine. What's cosine of 0? What? 1. Sweet. So what's the dot product here then going to be?
It's going to be equal to
The length of A, length of B times 1. So it's 8. Or even better, it's just 4 times 2 plus 0 times 0, which is still 8, right? So that's one extreme. If they're exactly pointing the same in the same direction, right? If they're opposite from each other, so what if this was negative 2, 0? What would happen? Oh boy. Yeah, then it would just be negative 8, right? Because what's the angle between them now? 180. What's the cosine of 180? Holy shit, see how it's all coming together. So a negative dot product just means it's gone beyond 90 degrees, because that's where the cosine starts to be negative. I like it. So it is length, but by this point you should understand that length can actually be negative in some, because it just denotes direction, right? Trig functions are based on lengths of sides of triangles. If you allow them to have negative lengths, you can draw them that way and do stuff, right? So negatives just mean direction. Okay, good. Maybe not in a few cases. I don't know. All right. Okay. Let me see. Let me make sure I didn't skip anything in this section. Blah, blah, blah. Yeah, blah. Wow, we're there. Kick-ass. So we got direction angles, direction cosines. We got projection and components, right, which we call scalar projection and vector projection. There's projection and components. We've used the word component before, so what's it mean now? Same damn thing. Just in some arbitrary direction assigned by some other vector besides x, y, z, right? Okay, so I definitely want to make it into cross product today. This is going to get kind of neat. That is one way to put it. There's a lot for me to throw at you. So let's see which way I decide to go. That was interesting. I don't want to do that. Okay. So I think I'm going to start here, and then here. What's here? This is here, and then I'm going to go that way. I like it. Let's see. How should I start off? Let's start there. I like that. Second.
It's not matrices, is it?
Yes, it will involve matrices possibly. So I will kind of show you a few things with matrices. Do you actually have to use the matrix stuff right now? No. But if you understand matrices, it gives you a way to remember and put together the equations you need. Okay. So very quickly, recall the dot product. I don't know if you guys remember this, but the dot product, we started off with a very physical problem, And then I somehow worked it so that it had another interpretation. So we started with the idea of you had to move this box this direction, I'd pay you money, and you decided to move it this way because it was easier. And then you had to figure out the angle between them and blah, blah, blah. You guys, if you were here, hopefully you remember that. So it turns out that the dot product is what? Remind me?
A1.
Okay, but using this idea with the angle.
Oh, length A times length B. Cosine plus.
Cosine thing. I like it. And then, of course, it's also A1, B1 plus A2, B2 plus A3, blah, 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 however many dimensions we live in. All right. I like it. I like it. All right, so I'm going to do a similar thing with cross product, believe it or not. Oh. And I don't know if you remember, what was kind of disappointing about this? What's 7 times 8? All right, and what kind of number is 7?
Prime?
It's a complex number. Sorry, a lot of answers there. So a complex number times a complex number has to be a complex number. There's no way to get something else out of that. Try it. Right? Think about it. If I multiply a plus bi times c plus di, I'm going to get something that I can write in that same form. And that's what I call closed. So complex numbers are closed under multiplication. They're closed under just about everything. This is kind of silly because I took 2 vectors and multiplied them and got a what? Scalar. So in one sense, that's not satisfactory. It's completely fine because we defined it. Screw it. You're like, why is it? Because I defined it that way. Nah. All right. But on another sense, it's like there's got to be another way to look at this. So the answer is also a vector. So somehow this is a closed system. Okay. So all right. So another way to look at multiplication of vectors, we call it a cross product, and you'll see why here in a minute. This is why I couldn't figure out which way to go first. But I want to start with the physical, show you something nifty, and then prove something, and that's my plan. I'm not going to be more specific than that. This is what's going to happen. So let's say I have these 2 vectors, A and B. And what shape does this make if I do this? A parallelogram. Take a minute and tell me what the area of that parallelogram is. If you know the vector answer, that's nice for you. I want to know, like, the scalar answer to that. I love those faces some of you guys make. At least you're showing. Some of my classes are completely stone-faced. Like, what do you guys think? Jeez. Oh my God. Somebody just carry you in here and plop you down? And then they carry you out? This should be... Alright. What's difficult about parallelogram related to a rectangle? Why is a rectangle area so easy? Whereas a parallelogram area, you've got to be very careful.
Rectangle is easy because you just do the side lengths of each other. But
What is the height of that rectangle?
the side length,
Yeah, let me call this something we're more used to. So the height's A. So the area is height times base. Always. For any, yes?
If we use parallelograms to measure area, parallelograms would be easy numbers, whereas rectangles are.
I like that. Well, let's not go there. I like it. I like proposing complete overhauls of mathematics, but not right now. So for this, that's easy because one of the given things is the height. Is one of the given things the height here? No. And let me actually, these are lengths here. Is that cool? They're vectors and lengths. Let me just make them lengths. So how do I figure out the height? So I got to give you an angle. So you got to hopefully define yourself that angle. And then what's the height? Well, let me draw that in. Here's the height's going to be perpendicular to the base. All right, so here's the height.
Sine of theta over
A is the what of this?
Hypotenuse.
hypotenuse. And think about this real quick. This is not exactly right, but this is a beautiful way to think about it. Sine theta is like the percentage of the hypotenuse that lies in the y direction. Cosine theta is the percentage that lies in the x direction. Not exactly, so don't come at me with shit, but that basically gets you through it. So sine theta times this will be this.
Isn't that projection?
I like, so you can bring it back into that. I love it. Right? You're projecting it along this, but we don't need all that for right now. You with me? So the height is just going to be a sine theta. So then what's the area of this parallelogram? What's the base? What's the base? I even gave it the letter B. B for base. So if you have the base and the height, you multiply them, that's the area. So I have the base, I have the height, I multiply them. That's the area. Get in there. You guys, so even if you know some of this, I don't know if you've ever been shown this, sometimes this is shown reverse. They say at the end, after they discuss cross product, they say, oh yeah, by the way. But I kind of like the idea of starting here, defining what it is physically, what it is. But this isn't the cross product, by the way. This is the length of the cross product. So this is what I'm going to define to be the length of the cross product. So when you find any cross product between two vectors, you have actually, and you take the length of that, that's the area of the parallelogram those would make. That's stupid awesome. All right. That's nice, Jeff. Now what I want to do, I don't know if you guys remember. If you remember, we started here, the physical idea, and then I did some math stuff to get here. So I'm going to do the same thing again. I'm going to do some math stuff. And this is really freaking awesome. Let it be awesome. I was excited earlier. Somebody came to my office and I was like, I just made a connection here that nobody ever told me about, and I'm really excited. So I'll try to calm down for a second. Here we go. All right. So now watch this. This is so beautiful, this complete picture we have now. The dot product is this. Get out of there, sign. The cross product's length is this. So real quick, what is this? Don't make too much out of it. No. Do you know what A dot B is? I wrote it for you. Do you know what A cross B is? I wrote it for you. Take a second and fill those in. Nothing major. It's just plug and chug right now. You're making too much out of this. Square that. Bam. Square that. Bam. I love this. This is just kind of silly that I've never was shown this. It's just beautiful. It all depends on the way your teacher teaches things. I really like this. I like that I'm able to show you this. Have you guys done it?
Yeah.
Oh, wait. So you guys should see where this is going. All right, what's A dot B squared? A squared?
Yeah.
B squared? Cosine squared theta. And what's A cross B squared? A squared. B squared. Sine squared theta. So can't you factor that out?
Yeah.
And what's cosine squared plus sine squared?
1.
So that equals a full A, B squared. Isn't that crazy? So do you see how in a way the dot product and the cross product complete each other and give you a full product? These are squared, that's squared, but that is the product of the lengths of the two vectors, right? So together they give you the complete product of the lengths of the vectors in a way. All right. Does everything I just showed you actually... I got to finish this out. There's some math we can do with this to give us another definition for cross product in this. Why is this definition not good enough? Okay, it requires the angle, but more importantly, is that a vector? No, it's a length of the cross. I don't even have the cross product yet at all in any form. I've just got the length of it. All right, so that's majorly not satisfactory, right? It's like, thanks, Jeff. All right, sorry, I'm not done yet. Get off my back. All right, so let's see. I'm gonna start this off, and then I'm just gonna say a lot of math happens because it's a bunch of repeated multiplications. Let's say that we live in 3 space, R3. So if we live in 3 space, A, I can call it, what can I call A? A1, A2, A3, cool? B would be B1, B2, B3. I like it. Cool.
Example.
No, this is doing some stuff. This is doing some stuff. Oh, yeah, okay. This will kind of work. Sure. Okay. This gets us there, believe it or not. So then, looking at what I've got there, A dot B, what would that be? So let me rewrite this. A dot B squared plus A cross B squared equals A squared B squared. Okay. So what's A dot B given those?
A1, B1. Plus
Beautiful. So this would be A1, B1 plus A2, B2 plus A3, B3 squared. Do you see why I'm going to say there's a lot of math and then something happens? Because I don't really want to do this. But if you did it, it would work out. You guys understand? I don't want to spoil the fun right now. All right. This is what I'm trying to solve for, actually. So I'm going to leave that alone. And on this side, what's this going to be? What's the length of A? What's the length of A? Who remembers how to get that? Oh, shit.
Everything squared in the square root, so it's...
So another way to look at the length of A, by the way, I don't know if I've said this to you directly, is to dot it with itself.
Yes.
Right? And then well, it's actually squared, right? But the length of A squared would just be A1 squared plus B, gather B, A2 squared plus A3 squared, times B1 squared plus, you guys kind of with me here a little bit? Everything I'm doing right now is not difficult. It isn't. This was weird to even think to do this. I understand that. But now I'm just looking at each piece, and it's just a bunch of just really basic algebra. B1 squared plus blah, 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 right?
Yes.
So if I FOIL this out, or whatever the acronym would be, and then subtract it from that side, you're going to end up with this. Let's see if I remember now. Oh, shit. You can do it, Jeff. Can you, Jeff? Yes, you can. Oh, give me a second. Let me see. I'm relying on my brain. Oh, yeah, you're doing fine, Jeff. This gets a little bit weird. You can do it. You can do it. Yay!
So this is from foiling and then subtracting it and then putting numbers together, basically.
Yes, I don't feel like it. You could all do it. So if you don't believe me, do it. But I think you should believe me. If you multiply this out, multiply that out, subtract that over, you'll be left with this. Now I don't know if you guys see the connection here. If I knew that this was what do you got, Jeff? 9 plus 4 plus 16. Somebody gave it to me like that. Can somebody tell me what vector A is?
Or plus or minus 3, plus or minus...
I got you. We'll say it's all positive. But yeah, good point. So it'll be 3, 2, 4, basically, right? And then somebody has to tell me direction, all that kind of stuff. I like it. So this isn't perfect because it doesn't. I'm not. The plus or minus is in there, but what this comes out to be is another kind of way to do this. So A cross B itself comes out to be A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2, A2B freaking 1. Now how do I, now this one I think, well, I'll show you a way to remember this. And you don't even have to understand much about matrices, to be honest, to do this. Can you, but before I do that, I want to tie this in. So I did the initial physical example to show you why it makes sense I want to define a multiplication to be this. It's the area of the parallelogram. How do you get areas of four-sided figures? It involves multiplication. So defining multiplication to be based on that makes sense. And then what did I do? A lot of math to see if there's another way to call it. And it comes out to be much, much worse than dot product. But of course, because the answer has to come out to be a vector. And is this a vector? Yes. 1, 2, 3 components. Notice how the first component, there's no 1s. The second component, there's no 2s. The third component, there's no 3s. Do you guys see that? Yes. All right. All right. It's just a little side note. So let me immediately show you something I just forgot. Let me think. What was I going to show you? Oh, yes. Okay, good. This is neat. Has everybody got what they want from this?
Yeah.
All right. You don't even really need this, to be honest. We're going to live off the results. Is that what's up? Oh, let me take this away. Everybody's got this. This is from a while back. Okay. This doesn't need too much. All right. Now give me a minute. Give me a minute. And just, if we brute force multiply this out. This is a little side note. This is